Good morning, everyone. Let's start our class today.
Good morning, sir.
Morning.
Sir.
So remember we talked about Cartesian product last time of two sets. Let us define it again. Let A and B are two non-empty sets. Non-empty.
Sir, did you share the screen?
Oh, I guess not. Thank you. Do you all see my screen now?
Yes, sir.
Yes, sir.
So then A cross B is the set of all ordered pairs such that X is an element of A and Y is an element of B. So for example, let B be the set of the element that contains the letter R and Q, and A be the set that contains the elements K, L, and M. Then A cross B is the set of all of these ordered pairs. The first element is coming from the set A. So X, the possible values of X are K, L, and M, and the possible values of Y are R and Q. Similarly, you can extend this definition for more than two sets. A cross E cross C. Again, we are assuming A, B, and C are some non-empty sets. Guess what? What would be the definition of X, Y, Z or Z? X is an element of the set A. Y is an element of the set B. And Z is an element of the set C. As we said, A cross B is the set of ordered pairs. Here we say this is the set of ordered triples. We call them ordered pair. And these are called ordered triple. And one good example for the Cartesian product of two sets, you can actually take the Cartesian product of set with itself. One prominent example and very useful example is R2. The real number set R times R. Again, XY ordered. Now XY both coming from the same set. The word ordered is more meaningful in this context. By an ordered pair, we mean XY and YX are not necessarily the same element. For example, here, 1, 2 is not the same as 2. And similarly here, you can take the Cartesian product of R with itself 3 times. Yes, which will be denoted by R cube, which is in fact R cross R. It's the set of all order triples. Each component of the order triple is a real number. Such that X, Y, Z all are real. Meaning we are multiplying 3 copies of R. Well, think about a real line which is horizontal and put one vertical to it. Call it x-axis, and this is its y-axis. Did I explain it to you all like this 2-dimensional plane is the same as this set? Can anyone recall?
Sir, I haven't been to last class, so I'm not quite sure.
Okay. Orko, do you think I explained these things, the equivalence of this plane and this Cartesian product of R with itself?
Yes, sir. You mentioned that we can have sets as elements of an another set, like a universal set or set that has smaller sets.
Okay.
And you also
So
took ordered pairs as elements.
Let me explain it again. So this is one copy of the real line. The horizontal one. And I think you all are familiar with representing number on a line. So I'm saying this is the horizontal line is on one real line. And the vertical one is another real line. The intersecting point is what we call the origin of the plane, and which is necessarily the point on the horizontal line that represents the number 0, as well for the vertical line. Now take a position in this plane. Let's say this position is P. Now simply drop 2 perpendicular on the 2 lines from that position. let's say this point is M and this point is N. Now take your measuring tape or scale. Measure the length OM. Let's say this OM is measured X unit. And the length OM is measured Y units. Then this ordered pair will give a representation of this point P, which says this point is exactly X unit away from the vertical axis and Y units away from the horizontal axis. Or in other words, this position P is X unit away from the vertical real line, which we are calling the Y axis. And this is Y unit away from the horizontal real line, which we are calling X axis. So we see like any point in this plane can be represented by an ordered pair of numbers. So now if we have some position at this point here, similarly, you draw to perpendicular. Again, let's say this is M dash. So let's say this is my P dash point. So then OM dash is X. And similarly, ON is Y. But in this case, as we are measuring from the origin towards the left, our horizontal measurement will be represented by negative of the length OM dash. So let's say this is minus X and Y. Similarly, for any position here, both measurement will be negative because X measurement is towards the left of the origin and the Y measurement is towards the downward of the origin. And here, X measurement will be positive, Y measurement will be negative. So it is clear that any point on this plane can always be represented by an ordered pair of numbers, and they're real numbers because all length are real. And conversely, let's say you are given this ordered pair 1 and 2. So that says go 1 unit in the positive direction of your x-axis and then 2 units upward along your y-axis. So let's say this is 2. So this position is your 1, 2 position, 1, 2 point. And similarly, let we are given a minus 1, 3 point. Let's say minus 1, minus 3 point. So from the origin along x-axis, you go 1 unit to the left and then 3 units downward. So this is your point or position, which is minus 1, minus 3. So the scenario is you are given a position in the plane. You can measure its distance from 2 axes and form an ordered pair to represent that position. And conversely, you are given an ordered pair, then you can find a location corresponding to that ordered pair. In this way, every position is represented by an ordered pair, And conversely, every ordered pair represents a point in the plane. So this R2 or R cross R is an algebraic or set theoretic representation of this geometric object, what we call the two-dimensional plane. Are you all following me so far?
Yes, sir.
Yes, sir.
Great.
Yes, sir.
So Cartesian product is really an useful construction in mathematical point of view. Especially you have seen a geometric object, which is a plane, is represented by the Cartesian product of two copies of the set of real numbers. So now you can interpret three copies of R, Cartesian product of three copies of R. What should this set represent geometrically? Do you have any idea?
A vector.
Yeah, we can say like each ordered pair is a vector. What sort of geometric objects this Cartesian product represents? Two copies
three-
represents a
A
plane.
three-dimensional space.
So
Three-dimensional
three-dimensional.
three-dimensional space. To visualize it, then this is my x-axis. That means we are taking one copy of real line in this direction and one copy of real line in this direction, call it y-axis, and up and down one copy of real line, we call it the z-axis. And their intersection is the origin. Coordinate of origin is 0, 0, 0, because it marks the numbered 0 on all these three real lines. And similarly, if you take a point one ordered triple xyz, for convenience assume x, y, z, all three are positive number, then you have a point in the plane like this, in the space, I guess. Let's take it this way. So this point is your xyz. This is your x measurement, 0 to m, let's say. This is your 0n is your y measurement in the xy plane. So this position is x, y, and 0. 0 in a sense, you are staying on the xy plane. No way above the xy plane or downwards the xy plane. So this z is 0. But if you go, let's say this is your point P dash. If you go upward P dash to P, then you get this third coordinates. So this is how an ordered triple represent a point in this space. And somebody said it is a vector. Yes, it is a vector. How? If you connect the origin with this position, let's draw one line segment. Then you get a vector.
Sir, can we call it a matrix with one column?
Yes, a vector is represented with a row matrix or a column matrix. Yes. These are different name of the same thing, but all this name has like different interpretation. When you say it is just an order triple, we just mean it is a point. But when we say it is a vector, then we think about the vector space structure on this set. When you call it is a matrix, yes, it is the set of all row matrices. which has 1 row, 3 columns. Yes,
Sir,
different perspective will name them differently. Okay, go ahead.
sir, the line, I mean the dotted line. The dotted line does the dotted line represent X, Y, Z, or the broad line?
The dotted line will represent the length of this C. How much you are going upward to reach this point P from the XY plane.
Oh, okay, sir.
Does it make sense now?
Yes, sir.
Great. So basically you are coming X unit along the OM unit or X units along this horizontal line, and then ON units or Y units along this vertical line, then you are here, and then you are climbing up like Z unit to reach here. X unit in this direction, Y unit in this direction, and then Z unit in this direction. And this is how you get this order to represent.
Sir, another question.
Go ahead, please.
Sir, in the bold line,
Mhm.
what point is actually X, Y, and Z? Is it the end of the line?
You can think about you can think it in this way, like it is the end point of this vector OP. Yes, but the question is, how do you get these 3 points? Think about you are walking along this line from this origin for X unit. You reach at the point M. Okay. From the origin, start walking for a while up to reach the point M. From here, you certainly change your direction vertically and then start walking parallel to this Y line. So you started here, reached at this point, and then parallel to the Y axis, you came up to this point, P dash. So how much you traveled along this line? X, this is the first component. And then how much or how long you traveled along this axis or parallel to this axis? MP dash, which is the second number Y. And then you certainly thought like, no, I'm not gonna roam along the plane anymore. Either I will go upward or downward. And then you went upward for a while and reached the point P. And the distance from P dash to P is Z, the third component. And this is how a ordered triple represent a position in this space. Do you get it now?
Yes, sir.
Mhm. And similarly, if you are given an ordered triple, let's say -2, 1, 3. So -2 means you have to go inward 2 units along the x-axis. And then Y unit parallel to y-axis. And 3 units upward. Wherever you stop is your destination. That's the point represents this order. So anyway, so Cartesian product, a very useful thing, at least we can represent our usual plane in a 3-dimensional space from the Cartesian product of real numbers. If you want to, you may continue to take the Cartesian product of arbitrary number of sets. Maybe will be meaningful in different context. For example, like we can take the Cartesian product of R copies of the real line or N copies of the real line, like this one. We'll say it is Rn. N copies of the real. In that case, we will say each element of Rn and n tuple x1, x2 up to xn, where all xi's are real. So here we said it is an ordered pair, ordered triple. In general, we call it n tuples.
Sir, what symbol did you use to mean x1 in general? All of the x's are belonging to the real numbers.
Right, xi's, yeah, where I is from 1 up to n. Yes, I should have written this part too. Yes, n tuples.
Sir, is there any specific way to generalize them like this?
What do you mean by the generalization here?
I mean, you didn't directly write all of them. You just write x1, and I can't see the entire symbol. That's why I'm kind of confused.
Okay. See, here we represented one dimension by x and the other vertical direction by y and the remaining one by z, right?
Yes, sir.
So in this case, like, I guess I don't have that many distinct letters. That's why I said this x1. I said this y y1 and this z as, sorry, x1, x2 and x3, just different naming. Do you see my points now?
Yes, sir. But in the last line, when you were trying to define the set R to the power n,
Rn, yes.
Rn, yeah. Here I can't understand what you used in the last part of the.
This one.
Yeah, yeah, yeah. This
Okay,
one.
okay. Let me write it down in full length. So I'm saying my x1 is any real number. And similarly, my x2 is also real number. And similarly, my xn is also any real number. That means we are taking the Cartesian product of n copies of the real number. This Rn is in fact R cross R cross. Oh, I guess I have written it right. R, which is said like different notations. Rn, n copies of R are multiplied together, or we are taking the Cartesian product of n copies of the same set, which is the set of real number. Just draw an analogy between them, like 3 copies. It is the set of an ordered triple where first element is coming from this set, second element is coming from this set, and third element is coming this set. Since all of them are the same set, we are saying X, Y, Z, all of them are coming from the real number set. And similarly, we're saying like instead of two copies of R, which is R cross R, which is the set of ordered pairs. In case of 3 copies of R, we said this is the set of ordered triples. Now we are generalizing this construction, saying like, oh, we can take the Cartesian product of any finite number of this set real numbers, and we are denoting it arbitrarily by n. This n could be 2, n could be 3, n could be 4, n could be 5, or whatever. If it is 5, then we have 5 components in our ordered, I don't know, what do you say, like ordered 5 tuples. Up to 4, you can say quadruples, but after 4, terminologies are not that well standardized. So Rn means like arbitrary number of R. We are taking the Cartesian product of an arbitrary number of the set R with itself. So here x1 means this is an element of this n tuple, which is a real number. That's why we said like x1 is a real number. Similarly, the second component of this n tuple is again a real number. That's what we said, like x2 is another real number. If you keep going in the same fashion, final element is xn, which is another real number. Does it make sense?
Yes, sir.
Anyway, if it seems like quite exotic or abstract, don't bother. You will find this guy in your linear algebra class again in the future. Okay. So this is our R2. We have explained it. 2 copies of R. R cross R. This is our plane. See, they're saying R cross N. See, not anymore R cross R. So R cross N. Do you see this geometry? The first,
Yes, sir.
The first component is changing continuously, while the second component is changing only in whole units, positive sense. So this is an N. So if X varies continuously on this line, that means X can take any real value, while Y, the second component, is getting only the value 1, 2, 3, 4, 5, and so on. 6, and you can have more, let's say 7, 8, and so on. So for all possible axes on this horizontal line, you are 1 unit up, then you are on this line. For all possible points on the X line, you are 2 units up, then you are on this line. So this is the geometric representation of R cross the natural number set. Let's see, what is the final one? So N cross N. So that means the points 1 and 1. So this is your 1, 1 point, which is 1 unit away from the both axes. This distance is 1 unit. Similarly, this distance is 1 unit. So here, if you take like 4 unit, 5, 4. So 5 unit along x-axis, 1, 2, 3, 4, 5. So you're here. 4 units along the y-axis, 1, 2, 3, 4. So this is the 0.54. So since in this natural number set, you have only the positive whole numbers, so you will get infinitely many of these lattice points. So this is another geometric representation of the set n cross n in the, and you see, like, this is a subset of R cross R because they are living in R cross R. This is also a subset of R cross R. So you can simplify it like this. This is contained here. This is contained. So drawings of some Cartesian product. Similarly, they talked about order triples. And arbitrarily, you can generalize your Cartesian product for n non-empty sets. The first component will come from the first set, second component will come from the second set. Oops. From here, second one will come from here, second set, and so on. And final one will be coming from here. That's what they said, like I1 is from A1. It's just a notation. I2, that means X2 coming from A2. Similarly, up to, if I is n, that means Xn is an element of the set A. And remember, this is an ordered n tuple. If you switch between two elements or two components of these n tuples, then you have a complete different tuples. And that way it is ordered tuple. Anyway, Cartesian product or Cartesian power, we already talked about that. If you take the Cartesian product of a set with itself n times, then it is an, which we used when our A is the set of real numbers. We say R cross R is R square, R cross R cross R is R cube, and n copies of R is R power n. They named it differently. It is the Cartesian power. So a to the power n, if A is a set, you say the Cartesian power of A, n. Did you all go through the all exercises in the previous section? All 50 exercises.
Sir, I didn't get the book. I searched for it in Google Classroom. Is it there?
Oh, no, it is not there. Didn't I share the book with you all?
Not that I recall, sir. I haven't received the book.
Or does anyone have the copy of this book?
Yes, sir. I have the PDF copy.
Oh, is there any way you can share among your fellow friends?
Sir, I need to have their email address. Otherwise, I can't share with them.
Okay. I guess.
Or you can just upload it in Drive and access
Okay,
make the link available.
Okay. I will distribute the link again as I did last time for the class recording. Okay, so my request is like strategy is you all individually make sure that you try all of these exercises. And if you find any difficulties, don't forget to share with us in class. We'll explain everything. But I want you to try first. So again, try all 16 exercises.
I'm sorry, sir. I'm sorry. I had another problem, sir. I tried to look at lecture 2, but the access to lecture 2 was not made possible. Is there any way that the access can be granted?
I shared it in Google Drive, right? With all of your
Yes.
email IDs. What
Yes,
could be the
sir.
possible reason that your access is denied?
I don't know, sir. গতকালকেও আমি try করলাম
Uh-huh.
and it did not work. I tried with both email addresses because I thought maybe it's a maybe my G Suite. Although I did not submit my G Suite ID, but I still tried with it.
Mhm.
This was still denied. I'm not quite sure why that is happening, but that is
Okay, I will check it again. Like for now, I really don't know. Like what could be the possible reason for
স্যার
denying
আপনি কি
access.
ব্র্যাকের ইমেল অ্যাকাউন্ট দিয়ে ড্রাইভে আপলোড করছেন?
Right.
আই থিংক আপনি মনে হয় অ্যাক্সেস দেন নাই, বা হচ্ছে মানে ব্র্যাকের আউটসাইড যারা তাদেরকে অ্যাক্সেস দিতে হবে আর কি।
Okay. Why don't you all have like a break email ID? Why it is not
We do
uniform?
have ব্র্যাক ইমেল আইডি, but
Sir,
you usually
yes.
send emails to our personal emails.
Oh,
Sir,
I
maybe
I got it from the university. They should have provided me like
Oh yeah, like on
personal
uses
IDs.
there's usually the people's personal email, not the G Suite, because that's
Okay.
usually created earlier.
Sir, I don't
Okay.
think G Suite is an issue. Maybe it just is made private. As I said, I tried with my G Suite ID, but it still gave the same results. I also thought that it was a G Suite thing. So
Mhm.
with my G Suite ID, but that wasn't working.
Okay. Let me next time share the link from my not institutional ID. Okay, I have one email ID which I am using last 12 years, I guess. I will share from that drive. Let's see what it how it acts. Okay, subset. Let's talk about a little bit of subset. As you all said in the first class, like set is a collection of objects. I just modified your definition. Adding an extra word, set is a collection of well-defined objects. Any sub-collection of a collection, if a collection is a set, any sub-collection of that collection is a subset. So the notation is something like this. We'll say like A is contained in B, and if it is not the case, then we'll say like A is not contained in B. Not contained in a sense, not completely contained in B, may be partially true. But by containment, will mean like everything in A is contained in B. For example, see, this is a collection of some numbers. This is another collection of some numbers. See, each element of this smaller collection is an element of the bigger collection or larger collection. So if you say this is your set A and this is your set B, so now tell me, is it true that A is contained in B?
Yes, sir.
It is true. But here, if this is your set A and this is your set B, and is it true that A is contained in B?
No, sir, it's not fully.
No, it is not fully contained because this element 3 is here, but it is not there. Even though 2 and 7 is there, that means it is some part of it is contained here, but it is not completely contained here. So when we say A is a subset of B, we mean each and every element of the set E is an element of the set B. Okay. And similarly, what about this? See,
Yes, sir,
there,
this is true.
yeah, it is true. even though they are the same thing, right?
Yes, sir.
Sir, I have a question.
Please go ahead.
For number 3, why do we not just use an equal sign?
Sorry, here.
Yes, sir. For number 3, why don't we just use an equal sign?
Oh, well, we could use the equal sign. Yes. So when you say like inclusion and equal, that means equality is a possibility here. It could be equal. Okay.
Oh, sir. So this is something that is done for both
Yes.
possibilities.
Less than or equal. It could
Right,
be,
sir.
yeah. Less than or equal, you are familiar with, like greater than or equal. So this is properly contained or they're equal. So a subset of B means one of the two things, one or the other, like A is properly contained in B, or it could be like, yes, A contains itself properly. That means could be the case A and B is the same set. So that's why this notation is standard. So now you can say like a set is its own subset because it contains all of its elements, right? So what should be the idea of equality of two sets then? If A is contained in B, or if each element of A is an element of B, and at the same time, each element of B is an element of A, this two condition implies what should they imply? Tell me.
The sets are equal.
They're the same set, right?
Yes, sir. This implies
Yes.
that both sets are equal.
They contains the same elements. So if they contains the same elements, they are same set. So remember, to establish the equality of sets, we will basically establish this two-way inclusions. A is contained in B, or A is subset of B, at the same time B is subset of A, and that will imply the equality of the two sets. So for good, for example, you know, like all even numbers are integers. So set of all even numbers is a subset of the set of integers. But not the set of integers. Not all integers are even numbers. That's why Z is not a subset of this. Now tell me, the null set, a set with no elements. It's called a null set, as we said last time. I mean, like at the first class, I guess. A null set is a subset of any arbitrary set. Can somebody tell me, like, from your ideas, don't have to be mathematically correct or mathematically sound. I'm saying any empty set is a subset of any arbitrary set A.
Sir, won't we need to define? Sir, arbitrary sets can also start after 0. So is that a possibility, or am I getting that wrong?
An arbitrary set can start after 0. I
Sir,
don't think like the set A should be a set of numbers always. It could be a collection of anything. It
Sir,
could be a
can you
collection
just
of anything.
sir, can you just repeat the condition for what it takes to be an element of a set, a
Right.
subset of a set?
Right. We said like, if each element of the set A is an element of the set B, then A is a subset of B.
Then the empty set doesn't have an element. So I think this notion that empty set is a subset of A is going to be an axiom.
Oh, okay. Okay. What you said, like almost correct. Almost correct. Can somebody else like explain it again? Is there anyone else want to speak up? You said like empty set has no elements. How can it have an element that is
Yes, sir.
an element of A,
the
right?
definition cannot be applied with empty set because it talks about element.
Right. So, well, if I say like there is no such element in the set which is not there.
Yes, sir.
There is no such element in this set which is not here. So in that sense, every element of this set is here.
That is also a condition for something to be a subset of another set.
Right.
Yes, sir.
So as far as you cannot deny the eligibility of subset, it's still a subset. Let me say it again. We say it like every element, if each element of the set is an element of B, then A is a subset of B. Now tell me, when A is not a subset of B? We know when A is a subset of a set B. Each element of A is an element of B. Now my question is, when the set A is not a subset of B? Just look at this example 2. Just look at this example 2. You said like A is not a subset of the set B. Why not? Because there is one element at least which is not here. That means there exists some element in the set A which is not an element of B. Do you all get it? Do you all follow me?
Sir, I am a bit confused still.
I'm saying, we are saying like definition of a subset is something like this. Each element of this set A is an element of this set B. Whenever X is in A, X is certainly in B. Then A is a subset of B. This is our definition of subset. Now my question is, when a set fails to be a subset of some other set, we said each element is an element of B. Each element of set A is an element of B. So what would be the violation of this statement?
There are some element in
There
A
are
that
some element in A that is not an element of B. For example, here, this some element is the element 3. Some element is here which is not an element here. So for a set to not to be a subset of other set is that there exists some element in the set which is not in the other set. So then we say A is not a subset of B. So is there any element here which is not an element of A?
No, sir.
No. That means like you cannot say like it is not a subset of A. To say this is not a subset of A, you have to find some element here which is not there. So in this way, we say like this is a subset of any set A. You don't have to prove like everything here is here. Rather, you are proving that there is nothing which is not there. Okay, we'll come back to this issues later on again. So we say like empty set is a subset of any arbitrary set A. And in mathematics, we say like this is backwardsly true. You really don't need any argument to prove it. As someone was saying, like we have to axiomatize the notion that an empty set is subset of any arbitrary set. To some extent, that is correct. Who did say it like? Hello?
Hello.
May I know the name like who said like for an empty set to be a subset of an arbitrary set A, we have to make an axiom.
Sir, I said that.
Sultanul Arifin, right?
Yes, sir.
Okay, great. I just wanted to know you.
Sir, I wanted to say something. In the
Oh.
previous class, you promised that you will talk about Russell's paradox in the next class.
Oh, okay, okay. I forgot that. Okay, remind me in the beginning of the next class. Okay.
Okay, sir.
Okay. So these are the ideas of subset. Empty set is a subset of every set. Fact 1.1. We tried to explain it. So I recommend you all to read through the text, read everything, and work out every possible exercise. Find any difficulties, share with us. We'll make it easy, hopefully. Now the question is like fact 2. We would like to see how many subsets of a set with finite elements are there. If a finite set has n elements, then it has 2 to the power n subsets. Okay? Let's do it in a very layman way. Let's say you have a set of 2 elements, AB. Okay, so this is your set A. So how many subsets possibly are there? You can construct it. A1, let's say. Is A1 is a subset of A?
It is.
It is, yes. A2, is A2 a subset of A? A3, is A itself? Is A3 a subset of A?
Yes.
Yes.
Yes, sir.
And A4 is the empty set. Do you think you can come up with another subset of A? Or these are the all
No, sir.
possibles? No.
No, sir.
Right?
No, sir.
So how many of them are here? altogether, let's consider the set of all subsets of A. So we call it as the power set of A. So this is another definition. Call it the power set of all subset of the set A. Not set of all sets, which will take you to the Russell's paradox. Power set. Set of all subset of A. So we can define power set P of the set A as the set of all sets B such that B is a subset of A. So this is how you write it. The power set of a set A. It is the set of all possible subset of a particular set of the set A. So what is the cardinality of this set, power set of A, when how many elements are there? 4, right? What is the cardinality of the set A in this case? 2. Okay, how about if A has a single element? How many subsets are
Sir, 2.
2, right? Then power set of A contains. This is a very intuitive, right? And very understandable. So here A itself and the empty set. So in this case, cardinality of A is 1. Then you got cardinality of the power set of A. Two. So cardinality 1, you got cardinality of power set to be 2. Cardinality of the set is 2. You got cardinality of the power set is 4. Just sort of 2 square. Now think A is a set of 3 elements. That means the cardinality of the set A is 3. The question is, what is power set of A?
Do we want the cardinality of power set A or the?
Yeah, let's construct it and then we'll count the cardinality. So first, the null set itself. There's a non-proper subset, and then proper set. Proper subsets are the subsets of singleton elements A. Let's list all of them. B and C. These are the all possible singleton subset of the set A. 3 elements, so 3 singleton subsets.
8, sir.
And then 2 element subsets, AB, BC, and CA. or AC. You know, like in a set, the order of element is not important. And 3-element set is the set A itself, A, B, C. And there should be no 4-element subset of the set A that contains 3 elements, right? So we have possibly listed all possible subset of the set A. So now how many of them we got?
Sir, 8.
8. So can we write 8 as a power of 2? Two to the power 3, right? So we got like when cardinality of A was 1, we got cardinality of our set is 2, means 2 to the 1. When A was 2, we got cardinality of the power set of A to the 2 to the 2. And when cardinality of A was 3, we got the cardinality of 2 to the 3. So as in young mathematicians, remember it is a common strategy in mathematics, like to prove any truth, start with these simple cases, like, and observe if there is any pattern. So what is our objective? To find the number of subsets of a set. So we started with a set with single element, and then counted its number of subsets. We found it 2 to the power 1. And then we experimented with a set with 2 elements. And we found that its number of subset is 2 power 2. So with the cardinality of the set, we found a pattern. In general, like we can conjecture or predict if A is, if there is n elements, could be 1, 2, 3, or whatever, then the number of subset of this set has to be 2 to the power n. So this is what we want to prove. So to prove this, we started with the simple or the simplest cases. And we found that, like, yeah, this formula works. And as a mathematician, once you see like there is a pattern, you may go for like more experiment to firm your observation, but that is not proof. Observation from the simplest cases give you better insight how to prove that truth, or how to construct a counterexample to prove that claim. Anyway,
So, sir, this can be called a scientific proof, but not a mathematical proof.
Not necessarily scientific truth. I don't know. You have not exhausted all possible experiments, right? So,
Yes.
so it is not scientific either. Anyway, I guess it is time to stop right here. It is 9:20. Anyway, before leaving, could you all tell me, like, the way I am teaching you all is being effective for you?
Sir, so far, yes.
Or if you have any suggestion, please don't forget to let
No,
me know.
sir.
because
You are
at the,
making sense.
at the end of the day, it is important, like what you are or what is your takeaway from my class. It is important. It is not important how much I know or how I try to dispense my knowledge. It is important, like how much it has been effective from your point of view. So let me know. Let me know if you have any suggestions. If I can, I will try to make shift. Well, so I guess we'll stop here today. If you are, do you have any question?
I'm
No,
just
sir.
I'm going to add in my email address in the chat in case anyone is sending in the book file, or is it can you
Sir, can you permit
uh,
me to, sir, can you permit me to share my email address to everyone so they can send me a message to asking me the book? I will send them.
Okay, let me.
or sir, is there a common source that you can book from? I can download it from.
Well, you can down. I think you will get this on LibGen. I mean, that's a big source of all kinds of.
Yeah, that makes sense. Okay. Thank
Okay. Who do I give the permission to share the email?
Sir, it's me.
Sultanul Arifin. Let's see. Sultanul Arifin. Let's see. Do I permit you? I don't know that either. Arifin, why don't I see you here on the list? Sultanul Arifin. Excuse me. No, Jom is giving me a hard time. Where the checkbox? Let's see. Fardin Rahman to everyone. Fardin, what is this link for?
Sir, this is the link for the book, but there are a few editions, so I'm not sure exactly which link it is, but I just gave a general link. I guess the students can find the appropriate book from here.
Okay, Sultanul Arifin, can you post your email here? I can share with you all that.
Sir, I posted it in the chat.
But I don't see it. Let me see. Why don't I see it here then? I have found the Fardin's one. Why not yours one?
Sorry, sir, it was not towards everyone.
Okay, so just send it to me or towards it. No problem. If you have no problem. Yes,
This is
Sultanul
my
Arifin.
this is my
Yes.
personal email address. So this is not the academic one.
Okay. So please, everyone get this email address and shoot him an email address so that he can share the book with you all. I will share that either.
I have the latest edition, so I think that will be better for them.
Okay. Let us cut short here today. Talk to you day after tomorrow. Okay.
Assalamu alaikum.
Walaikum assalam.
Assalamualaikum, sir. Goodbye.
Walaikum assalam.
Assalamu
Goodbye. You all
alaikum,
have a good
sir.
day.
You
So
too,
you're
sir.
not going to
Thank
take
you.
attendance today?
Oh yes. Sorry. Let's do it.
Well, some of us left already.
Okay. Okay. In that case, let me give attendance for each of you, all of you. Okay. You can leave. So all are present today.
Assalamu sir.
Walaikum assalam.
Assalamualaikum, sir.
Walaikum assalam.
Thank you, sir.
Mhm.